The NilePDT demo. This demonstration presents NilePDT, a phenomenon detection and tracking framework inside Nile. Nile is a data stream management system developed at Purdue University. We present the design of NilePDT and its applications in sensor networks. Many sensor network applications are interested in detecting and tracking phenomena that appear in their fields of interest. Examples of interesting phenomena include the spatiotemporal propagation of pollutants, for example an oil spill region or gas leakage cloud. We define a phenomenon to be a group of sensors that show similar behavior over a period of time. NilePDT uses a real sensor network platform as its underlying source of data streams. The functionalities of NilePDT are split between the Nile server and the NilePDT application client. At the server side, Nile detects phenomenon candidate members and tracks their propagation incrementally through specific sensor network operators. Phenomenon candidate members are processed at the application side to detect phenomena of interest to a particular application. A graphical user interface is developed for both the NilePDT client and the Nile server to visualize the phenomenon detection and tracking processes. Our demo has two setups, one where the sensor network is simulated and the other uses real sensors. When we run the demo using a simulated sensor network, the client GUI represents each sensor by a circle that reflects its location in space. Sensors are spread all over the space arbitrarily. The client can keep track of both the original phenomena that are computed offline given infinite resources and the phenomena that are detected by the system. The client GUI shows the efficiency of the system in two aspects. First, the response time of the system. Second, the accuracy of detected phenomena. The response time is identified by how far the detected phenomena propagation lags after the original phenomena propagation. The accuracy of detected phenomena is measured by the number of reported sensors relative to the total number of sensors that participate in a phenomenon. At the server side, we make use of a new query operator, the SN join, or the sensor network join operator. SN join is a generalized, similarity-based binary join operator that is designed for sensor network applications. The main challenges in realizing SN join are the following. First, SN join is a similarity-based join. In other words, it is not necessary that sensor values match exactly. Sensor readings that are close to each other in value will still join and produce an output tuple. Second, and most interesting, is the query processing with relevance feedback capability. SN join uses a relevance feedback mechanism that guides SN join as to which streams to join in order to increase likelihood of producing binary join output tuples out of the huge number of sensors in sensor network that have similar behavior. In other words, guided by the detected phenomena, NilePDT operators tune query processing towards sensors that heavily affect the monitoring of phenomenon propagation. The server GUI demonstrates the system's internals and shows how the query plan is executed. The query plan along with the relevance feedback are displayed graphically, and the incoming tuples keep moving up the query plan from one operator to the next. The server can be executed in slow motion, and the number of sensors is reduced for the sake of demo clarity. Our demo hardware consists of a 5x5 grid of temperature and light sensors that are connected to sensor platforms developed at the Pervasive Computing Lab of the University of Florida. They have a flexible, stackable architecture consisting of a processing module based on the Atmel Atmega 128 microcontroller, a communications module based on the Crystal LAN CS8900 Ethernet controller, and an interface board to connect various sensors and actuators. The driver bundle for a sensor is stored on board the sensor platform. When a sensor platform is powered up, this bundle is uploaded and installed on the fly on the OSGI framework running the Sensor Network Manager middleware. These bundles transform the physical sensors connected to the sensor platforms into software services, which are then accessed by NilePDT. NilePDT detects and tracks various forms of phenomena from sensor data as we apply a heat source on the sensor board, or as we wave our hand to produce shades and light effects on the sensor board.